is to quote from Art from his memoir published in the Annual Review of Energy and the Environment a few years ago. And Art writes that my most productive and stimulating collaborator at DOE turned out to be Joe Rome. So, Joe.
Now you embarrass me because I was coming up here to roast Art. Because I've been reliably informed that I can't do that tonight because I'm speaking now. I guess the central question my talk will answer is why am I here? Or why am I here today? And the short answer is that Amory Lovins couldn't do it. As an aside, there's some good news and bad news. The bad news is that I'm not as smart as Amory. The good news is that my slides are easier to understand. There's some, I guess, reverse correlation there. I don't know what it is. It's there is a longer backstory because I think everyone else is up here because of something Art did, and I'm here because of something Art didn't do. Some of you may watch the TV show Lost, and the best part is the flashbacks to the character backstory that reveals the irony and the karma and the poetic justice of the situation. Physicists, of course, don't believe in karma and fate, much as they don't believe in intelligent design, creationism, and, say, economics. The first time that I talked to Art, I think, was about 15 years ago. I had been working for Peter Goldmark at the Rockefeller Foundation and talking to a lot of the leading experts on a variety of issues in the country, and they persuaded me that the future problem that the world was going to face was enough amounts of sustainable energy to avoid global warming. And so I wanted to get more expertise and training in energy. And I talked actually to Princeton, and I talked to Art, and the Princeton story will have to be another day. Art didn't hire me, and I really owe everything I have accomplished in energy to the fact that Art didn't hire me. Although that isn't what the irony is, and I think Art knows where I'm going with this story. Art didn't hire me, but Amory did. And as a direct result, I ended up at DOE in 1994. And that is a long story. I will perhaps put on a podcast someday. But the fact that I went to DOE led to the 5 Lab study. It led to my becoming acting Assistant Secretary of Energy, as you heard. And I will just read from Art's biography. From 1994 to 1999, Dr. Rosenfeld served as Senior Advisor to the U.S. Department of Energy's Assistant Secretary for Energy Efficiency and Renewable Energy. So you perhaps can see where I'm going here. So 6 years after Art refused to hire me, he was working for me. So this is, in fact, a great country. Of course, Art doesn't really work for anybody, but this is my story. Anyway, there are students here, and so there's obviously a moral to this story. Not, what your mother said about, one door closes, another door opens, because I'm hesitant to generalize from just one data point. So I would just say that if you want to speak at Art's 90th birthday symposium, ask him for a job tonight and hope he says no. Now I should perhaps get to my talk. When Hurricane Katrina hit the Gulf Coast, my brother had a house in Pass Christian, Mississippi, and 1 mile inland it got 20 feet of water, and it just got me really thinking about climate change and what I should be doing. And I spent a lot of time talking to leading climate scientists and energy folks and political folks to sort of better understand the issue. I spent a lot of time, as many people know, talking about climate, but more time talking about climate solutions. And let me just, a lot of what I was going to say today has been said, so I'll kind of leap through this presentation. I think that although there's a lot of uncertainty in what's going to happen, I think that there's a lot of high probability as to what's probably going to happen, mainly because we're doing nothing. And doing nothing adds a lot of certainty to emissions, concentrations, and impacts. Clearly, most warming goes into the oceans and the poles. Warming up the oceans just makes hurricanes worse, and I think super hurricanes Category 4 and Category 5 are now the norm. I think that will become increasingly clear. I spent a lot of time talking to some of the leading climate and hurricane experts. I actually, although I've done energy policy for 15 years now, I did my PhD thesis with Walter Monk at the Scripps Institution of Oceanography and Physical Oceanography. I have been persuaded by Hansen and that if we sit on our hands for another 10 years, it's pretty much a done deal that Greenland is going to lose its ice mass, and that's 7 meters. And if we were to sit on our hands for 20 years, we're going to lose a lot of Antarctic ice, and that's another 20 meters. And then the only question is how fast. I mean, there's two questions. Is it irreversible? And the answer is probably yes at some point, and how fast does it go? And I am persuaded that the more CO2 you put in the air, you get up to, maybe 0.2 to 0.5 meters per decade, and there's no, one doesn't really adapt to that so much as suffer from it for centuries. I will say that a lot of the debate in this country has been premised on a disinformation campaign to make it seem like the scientific consensus overestimates what's going to happen, when I don't think there's much doubt that the scientific consensus, at least in the IPCC, underestimates what's going to happen. I think the short answer on the solutions is the only hope to avoid catastrophic climate change is to deploy technology now, which is certainly my reading of the Wedge's paper. I put RE here not because of renewable energy, which Art would have me not do. The first three, this is the Rosenfeld effect, deploy efficiency, deploy efficiency, deploy efficiency, and then get around to renewables if you still need to. This is a Levitas paper, Science 2001, 90% of the warming goes in the ocean. I just put this headline up from Science. Scientists' fears come true as hurricane floods New Orleans. I'm afraid that first line there is going to become pretty standard this century. Scientists' fears come true. Let me just put up this chart. This is the June to November sea surface temperature from 1880 to 2003. It's a 5-year running mean. I have used Fahrenheit here. And of course, this is volcanoes, and this is aerosols and volcanoes. But the key point is, since the mean here, we've gone up about 0.8 degrees Fahrenheit in the last 30 years. This is the number of tropical storms. And the number of hurricanes is quite reliably about half of that. It's a very good correlation, but the particularly scary thing, of course, is that this number is just going to keep going up. In the next 30 years, it's going to go up as much as it went up in the last 30 years, and then it's going to go up again and again and again and again. And there's been a lot of effort to blow smoke into this subject, but it's really just smoke. This is actually June to November. It's the same temperature data plotted against 5-year running mean of the number of Category 4 and 5 storms, a pretty good correlation. And again, pretty worrisome. We had 2 years ago 4 Category 4 and 5. Last year we had 5, including 4 Category 5s. And these are the city destroyers. I mean, it's the Category 4 and 5s that really do all the damage. Half of all the damage done to the United States by hurricanes in the past century were done by 5 storms. I won't go through this. This is just, there's a lot more statistics behind this. This is Kerry Emanuel's stuff, and I just urge people to read it. This is just storm intensity versus, again, sea surface temperature. The correlation is exceedingly good. There's been, as Henry said, just a major disinformation campaign. It is amazing that the head of the National Hurricane Center can say that the best correlation with hurricane activity is sea surface temperature, and then turn around and say that it has nothing whatsoever to do with global warming. It would be less amazing until you find out that you can become the head of the National Hurricane Center in this country and not take a single class on global warming. Not required to be certified as a meteorologist in this country. The head of NOAA, a similar absurd line. Sea surface ice, I just put this up here. This is sea surface ice extent in the Arctic. over the past 30 years. I just put this up for two reasons. The amount of ice loss in the last 30 years has been equivalent to 3 Californias in size. It's large, but the most interesting thing to me is that it is larger than in any of the 19 IPCC models. This is from the Bjerknes Center, likely due to unresolved feedback processes. Speaking of things that aren't modeled, people used to think it would take 1,000 years for the ice sheets to melt, but that was based on just heat transfer and melting. Now we know the ice dynamics allows melting in the summer to flow down to the bottom, lubricate the ice sheet, and have it melt out. We also know that the outlet glaciers, which are floating, can basically disintegrate, and ice sheets can just start flowing very quickly. I think, and I'm just, I'm not saying that there's a lot of certainty here. When you start getting to unmodeled feedbacks and processes, I think it seems pretty likely, based on the literature, that somewhere between 500 and 700 parts per million, the ice sheet disintegration becomes irreversible. There are many irreversible features of this. As the ice sheet's 2 kilometers thick, as it shrinks, of course, it's going to lower altitudes where it's warming. So there's no question, at some point when you pass a point, you just don't go back across it. So the reason I titled this 100 Katrinas is, I think that future hurricane seasons are going to be somewhere between the 2004 and 2005 hurricane season, and probably one on average making landfall each year. It's kind of a random thing whether it makes landfall. I think one can't be certain what sea level rise is, but I think one should expect or plan for somewhere between 0.5 to 1 meter sea level rise by 2050 and 2 meters by 2100. I'm sure this won't be in the 4th assessment, but my guess is by the 5th assessment, numbers like that will be pretty standard. I just put this up here because when you combine a sea level rise with the super hurricanes, you end up with a whole bunch of things that look a lot like New Orleans. It's hard enough to protect coastal cities from flooding. I would say it's almost impossible to imagine rebuilding them once you know you're going to keep getting Category 4 and 5 hurricanes and you're going to keep getting sea level rise. So we'll just triage our major cities, and probably the first to go will be New Orleans. Let me just briefly talk about one feedback that's pretty clear. The amount of carbon in the tundra is equal to the amount of carbon currently in the atmosphere. And a very nice paper by NCAR out in the fall. Somewhere at 550 parts per million, you lose 60% of the tundra. And this, by the way, this is carbon, but much of it's methane. And if it goes as methane, obviously that's a lot worse. I asked the author of the paper, Lawrence, whether they had modeled the feedback in this analysis. And the answer is they haven't. And in fact, they're not even planning to model the feedback of the carbon losing, of the tundra losing carbon in their own NCAR model until the 5th assessment. And this is the permafrost melting. This is a sinkhole going. This is trees that are supposed to be vertical becoming drunken. This is what happens if you get to 690 parts per million. You lose all of these lighter colored tundra area, and you're just left with the blue, and you've lost 90% of the tundra. This is actually, there are very few models model all the feedbacks. Dr. Chu sort of mentioned one. This is the Hadley model, what you can do, how much you can emit if you want to stabilize at 550. This is gigatons of carbon without feedbacks and with feedbacks. The feedbacks totally constrain all your behavior. We're at 380 parts per million rising 2 a year. I would just assert that if we get to 500 and rising at any significant rate in 2050, you can just bet on 700 or 800. So global emissions really have to peak in 2025. I mean, you just can't wait that much longer. It gets to the point of how much you can overshoot. You can't overshoot so much that you cross some irreversible positive feedbacks. So that automatically makes, what I say is sort of carbon becomes a very clarifying concept. You have to cut CO2 emissions greater than 50% by 2050, so you just have to stop building traditional coal plants and have average new cars. I mean, if you have 50% more people and 3 times as many cars, it's kind of obvious what the average MPG has to be in 2050, and this is let me just, you saw the coal numbers. I just used another chart from David Hawkins. This is gigawatts of coal plants being built per decade. Certainly, if you get out in this area, the amount of carbon emitted by these plants over their lifetime equals the amount of carbon emitted by all the coal burned since the dawn of the Industrial Revolution. The sad thing is it's $1 trillion of misallocated capital. Someone just has to stop it pretty soon. I want to disagree with my good friend Dr. Sokolow on one point. All unconventional oil is an unmitigated climate disaster. Tar sands is doubly bad because you're diverting natural gas that would have come to this country to displace coal and used it instead to make a carbon-intensive fuel. But coal to oil is an unredeemably bad idea. It has double the CO2 emissions, but if you capture the carbon, it's still just regular diesel fuel. It can't be a wedge, because you could essentially have unlimited growth in diesel oil consumption and you'd capture the carbon. In fact, it's doubly bad because you displace, we don't have an unlimited reservoir of carbon. You would end up displacing carbon from much better places, things to use it for, which is making zero carbon electricity with IGCC and burying that. So unfortunately, this may well happen. The Chinese are certainly quite into it. People are going to have to grow up within the next 10 years and just ban it outright. Enhanced oil recovery, also not a great idea and should not be valued as geologic storage. The thing that they're going to do in California to take CO2 and use it to get more uneconomic oil out of the ground may be a great thing economically, but it hardly constitutes a really great idea from a global warming perspective. I'm going to skip to Farrell and Brandt paper. There's a very fine paper that they're coming out with on this. Let me go to, just to reiterate what Henry said, this is public energy R&D and private sector energy R&D. And as you can see, they're both pretty bad, but private sector is worse because the country has, started deregulating and people become more short-sighted in this country. I come to the state of California. It seems I feel obliged to say something bad about hydrogen. There will be no hydrogen wedge. It's just for all sorts of reasons. I doubt anybody's going to build a hydrogen car anyone in this room would want to buy. They would certainly take a very long time to deploy. I like Reinert's quote, "If I told you never, would you be upset?" I think Toyota gets this. But I again commend people to read Alex Farrell's July '03 science paper. You wouldn't divert valuable low and zero carbon resources to make hydrogen to displace hybrids when you could use that to stop building the damn coal plants. You have to, A, stop building the coal plants, and B, you then have to shut them down and replace them with zero carbon resources. You're not going to squander natural gas or renewable electricity on something boutique like hydrogen. I'll just briefly say, you can read my Scientific American article out this month. The car to future is almost certainly the plug-in hybrid. When I was at DOE, we weren't supposed to pick winners and losers. We had to like all technologies. We've run out of time to like all technologies. We have to pick all the winners now, or we are certainly screwed. Now, the first, because we've done nothing for 3 decades on vehicle efficiency, the first thing we should do is vehicle efficiency, and perhaps the second and third thing we should do is vehicle efficiency. But when we're done with that, when we've switched all over to hybrids and hopefully have 40 to 60 mile per gallon CAFE, you then just add a battery to your car. You just switch the power battery with an energy battery. It can go all electric for 20 miles. People don't drive much more than 20 miles a day. You drive to work, charge up, drive home, charge at home. Displace half of gasoline. You don't need a whole new infrastructure. You can blend in cellulosic ethanol. It's great with a carbon cap because then you're shifting emissions from 200 million small, difficult to regulate mobile sources into 1,000 stationary, large, easy to regulate sources. And of course, if you build this car, you will never build a hydrogen fuel cell vehicle. Why? Because the whole premise of the hydrogen fuel cell vehicle is that you're going to take zero carbon electricity, buy an expensive electrolyzer, convert it to hydrogen, buy an expensive infrastructure, ship the hydrogen to a fueling station, squeeze the hydrogen on board a car, run it to an expensive fuel cell just to convert it back to electricity to drive an electric motor. You would throw away 75% of the original, very valuable zero carbon electricity. You would buy 3 incredibly expensive pieces of hardware, and it's just the worst conceivable idea. And I'm not going to assert that just because it's a bad idea, it won't happen. But I will assert that before we could contemplate doing it, people will be so desperate to reduce carbon dioxide that the whole effort will largely be abandoned. I put up Art's slide, which everyone has seen, not just to give him his due, but to just make the point. Most of this is deploying existing mundane technology. It is not about fusion. Fusion or hydrogen or lots of breakthrough technologies you can imagine could be a good idea after you spend a lot of money doing this, and maybe even at the same time. But if you don't do this, the other things don't really matter that much. This administration has, you know, as Henry said, they get away with murder. They hate technology. They're sort of known for liking technology, but in fact, this is a quote. You can get it online. Abrams said, "No technologies currently exist to significantly cut emissions." This is the Secretary of Energy in 2003. This is the EPA administrator. Are we going to tell people stop driving their cars, or do we start investing in technology? It's this false choice, and that's why I've said that this administration doesn't like technology. They only like new technology. And once the new technology becomes existing technology, they go back to hating it. You know, just to reiterate what Henry said, they've shut down the regional offices of DOE, which are the best for deploying technology. They're going to zero out one of the best programs the Department of Energy ever did, which was the Industrial Energy Efficiency Program. You've seen the budgets. And it should be pointed out, not only did we have Henry's depressing numbers about efficiency, but while we were cutting efficiency, we're boosting all this money going to the hydrogen fuel cell vehicle program, which, as I say, is largely, let's just say it's 80 to 90% a waste of money. But the Secretary has an understanding of science and scientific processes. Just quickly, I'd just like to say what technology breakthroughs in the past 3 decades have transformed how we use energy today. The answer is there haven't been any. I still wait for somebody to call me on this one. Fundamentally, it isn't new. It has taken 25 years after commercial introduction for primary energy form to attain 1% of the global market. The point is, whatever technologies we got now, that's what we're stuck with to avoid catastrophic warming, because again, we have to peak in 2025. I just, you know, the wedges you've seen, I think that it's a very important concept and idea, and I certainly like to use it as much to say that I think which the point of it is that existing technology can do the job. I also use it for the converse which is new technology can't do the job, because it was written in 2004 with a start date in 2005. We were at 7 gigatons. They're each a gigaton wedge, so you need 7 of them. I just assume we're going to do nothing whatsoever as long as you know, George Bush well, as long as Dick Cheney is largely running things. So you can't start till 2010, which gets you closer to 8 gigatons, so you start to need 8 wedges. I've just picked mine. Some of these aren't exactly the same as Rob's, but they're frankly the only ones that I really believe in. These are, and Rob usually says this, these are immense scale problems. The amount of carbon capture and storage needed just for one wedge, 800 gigawatts of coal, is equal to the amount of carbon dioxide into the ground as oil flowing out of the ground. It by itself is an unbelievably substantial engineering enterprise. All of these are really difficult. There isn't political support for a single one of them. If you wait until 2020 to start this, you know, you're going to blow past 650 and then get into the feedbacks. So I just, this brings you to, you know, Hanson's whole point is this is the last 400,000 years. This is sea, this is time. This is the Eemian interglacial. These are the cold periods. We had about 20 feet higher sea level rise here when we were about 2 degrees centigrade warmer than pre-industrial levels. And that's what probably 2 total means. 3 gets you here, which is when we had 25 meters higher sea level rise, and 4 degrees gets you here when we had 70 meters high sea level rise. These numbers are, this is not my favorite chart because it's not exactly right, but the numbers on sea level rise are basically correct. And I think that again, if you cross over the thresholds, I think it gets to be a point where it's very hard to get back. I use a quote. this is the last quote in Elizabeth Colbert's book and articles. It may seem impossible to imagine the technologically advanced society could choose, in essence, to destroy itself, but that is what we are now in the process of doing. I just add that when future historians write with justifiable bitterness about our time, they will certainly judge the Bush administration very, very harshly, but I'm not so certain the rest of us are going to fare that well either. This has been a catastrophic failure of messaging and everything else by the scientific and energy community. You know, there's a lot, there will, in the future, you know, obviously the people who are actively trying to make bad things happen will get blamed, but I just think that it is incumbent on everybody who understands this to go out and talk about this as much as possible. Personally, I don't understand why the students aren't marching in the streets on this one, because it is your climate that is going to be utterly ruined. I will end with one slide here, which I normally put earlier in the talk, but this is private sector R&D investment in health versus energy, and I just put this up here because of the irony that at least people will live long enough to see how badly we've screwed things up. Yes, and I thank Dan Kamen for these various slides here. I also wanted to end on it for another reason, which is that you know, I appreciate what John Holdren said about cloning art. I'm going to just roughly do a even back of the envelope, just in my head, estimate that art is about half a wedge. So just somewhere between 14 and 16 clones, if we could get them up to age quickly enough. Otherwise, they just kind of spiral exponentially as you wait. Thank you very much.
Joe, what do you think the probability is that a hurricane of Category 3 or greater will hit New York City in the next 10 years? And also, could you discuss the implications of that?
You've been watching either the Weather Channel or the Discover Channel, which has been positing this scenario. I think the worrisome thing about hurricanes, which I didn't go on at length about, is that they're unlike other weather phenomenon in that they are threshold events. You really don't get any hurricanes when sea surface temperatures and down, let's say, to the mixed layer of a few tens of meters aren't above 26 degrees centigrade. And so as you warm the Earth, as you warm the oceans deeper, I mean, there's two important effects to understand. First of all, you spread the warming out in 2 dimensions. And you also spread it out temporally. So in this case, you get Category 5 hurricanes in July, the first ever recorded we had last year. You get the longest lasting hurricane in December last year, and the longest lasting hurricane that started in December and ended in January. So you have longer hurricane seasons. You have hurricanes in places they didn't used to be. 2004, first hurricane in the South Atlantic. People didn't think that could happen. I mean, I'm sure there were ones, you know, millions of years ago, but the first in recorded history. We had the first hurricane in recorded history to hit the Iberian Peninsula last year. So spatially, obviously, they're going in all different places. And the last key point is that as you warm down deeper, which is where the warming is penetrating, if you want to maintain above a Category 3 for any length of time, you have to, the stronger the hurricane, the more it churns up water that is below the mixed layer, and that is a self-limiting factor for hurricanes. But as you increase the amount of, this is the North Atlantic, this is a warming signal North Atlantic, this is down in meters. As global warming just continues and continues and continues, and you get more and more water, warm water below 50 meters, you're going to get less of the self-limiting of hurricanes. And so it just becomes more likely that sometime a Category 3 hurricane lasts long enough to amble its way over to a city that does, you know, as you know, Katrina-like damage to New Orleans. Because in New York City, you've got wind tunnel effects, you've got the subway system when it gets flooded. I mean, the Discovery Channel just did a show on this, and I know the Weather Channel is doing a show on this. So And clearly, as sea levels rise, it just becomes impossible to protect. And that's when you get to, frankly, a rather grim form of urban triage. So, I just think, again, you deal with this all in the next 10, 15 years, or, you just face a very unpretty picture.
Bill Fulkerson. Joe, let me ask you an interesting question that also relates to Steve Schneider's talk and to John Holdren. John Holdren said, the probability of stopping at 2 degrees is about 20%. Well, it's a guess. But, and Steve Schneider pointed out this bump that may be above what you'd like to stop at. And I am reminded of a very interesting paper that, that was written at Lawrence Livermore National Lab, another lab down the road, that was authored by Edward Teller and Lowell Wood. And what they proposed was that you could offset temperature rise by particles in the stratosphere that could be put there easily and cheaply and would only last a few years, so that it's a reversible idea. And if you did this for the case, the guess is that if you look at this problem of controlling our gluttony and the gluttonies of India and China, and making a world system that really works within the time frame you're talking about, the probability is low. And
Well, I would say it's 0 if you don't try. So
no, absolutely try. We ought to have the wedges, the intensity of effort, but it's very likely it won't work, in which case you need a backup. And I don't see any research or any effort going on this offset idea.
Yeah, let me just, I guess my comment on that, it's from the perspective of morality, it's, I think, very dubious to say that we could do it, but we're not going to, because that's just the kind of human race we are, and so we're going to start spending a lot of money on these pine. No, but it comes down, I'm just saying, let me put it this way. The people, Bill, the people who, one can articulate that view in a very well-meaning fashion, but the people in Washington and who run this country and make their arguments, who advocate for spending on adaptation and who advocate for spending on geoengineering, do so principally to use as an argument for doing nothing now. Is it conceivably possible that there might be some geoengineering solution that could avoid the worst of this? I would certainly. Who could possibly say that there's no chance whatsoever? But I would just assert that if you don't try really hard to stay as close as possible to 550, that your adaptation and your geoengineering efforts are basic, I won't say hopeless, but they just become exponentially hopeless. And I would be all for spending that money. I don't think any of us who believe in mitigation are against spending that money. I would just say that you have a lot of people out there talking about adaptation and geoengineering who in fact don't spend a nickel on it, and anyone who really believed that adaptation was the way to go with global warming would strengthen the levees of New Orleans to withstand a Category 5 hurricane and 3 feet of sea level rise. So the fact that they're not doing that shows that they don't believe in adaptation. They just believe in rhetoric that tries to convince people we don't have to do anything now.
Messenger with the Energy Commission. I was struck by your statement that you think that existing technologies now could help us generate at least a couple of wedges. And I want to ask you, perhaps as a political scientist more than as a technologist, could it be that the problem is not technology, but the fact that we don't have institutions capable of dealing with this problem? And that maybe we should spend less time worrying about getting technological solutions to this problem and spend more time getting the scientists to focus on the institutional problems of convincing the next generation of the people in the world that this is a serious problem that requires a change in the way that we organize ourselves and our economies.
Well, no, I mean, I basically agree with that. I mean, I certainly would be, I would go further. I mean, I certainly would be happy to stop all basic research in this country if you gave me my top 3 policies and do it forever, you know, because, you know, I think that this is, you know, there's no question that I would say the next 10 years are as important to the human race as any 10 years in history, including 1935 to 1945, and that this is going to be the great challenge for the scientific community, the policy community, the political community, and various generations that are represented in this room. And I don't think that there's an easy answer. I know that a lot of smart people are thinking very hard about this, but I think it is certainly, I spent a lot of time in the last 15 years touting the technology solution, and I think that it has been cleverly twisted by the opponents of action into what is somewhere between a placebo and a smokescreen, and so I try not to do that anymore. You know, there is no question that it is deploy existing technology now, or you know, it doesn't really matter what you do 20 years from now.
One last question. Oops, sorry, 2 last questions. 2 people who have mics.
Hi, Joan Ogden from UC Davis. Hi, Joe.
Hey, Joan.
How you doing?
I'm doing well.
Okay. I just
My
wanted to-
co-author.
I just wanted to make a couple of comments on your comments on hydrogen and other long-term fuel options. Let me first say, I think, like many other people in this room, the first course is efficiency. Everything runs through efficiency, improving efficiency of vehicles and the rest of our energy economy if we're going to get anywhere, no matter what we run cars on. But in the spirit of looking at your last graph, where you looked at energy R&D plummeting, the private sector, the public sector, it's all going down. There's a small pie. Then thinking about the concepts people were talking about early about insurance, you know, we can't afford not to have insurance. Having looked at a number of these technologies, all of them have questions surrounding them. In the long term for transportation sector, let's say electric batteries are one, fuel cells and hydrogen are another, biofuels are a third. Each of those could get us, once we push efficiency, they'll all be more doable, they could get us low carbon. I think at this point, we don't really know the answer. We do know the answer as far as efficiency. We know policies we need to do. In the longer term, I'd like to make a plea more to push up the end of that R&D curve so we can afford to try all these things. I think we need to go for all of them.
Sure, and you know, you know, I'm a big fan of you know, doing clearly, even if you do a lot of stuff aggressively the next several decades, you need a whole bunch of new technology after that. You know, my main point is if you don't do the you know, wedges now in 3 decades, it doesn't really matter what. I don't say it doesn't matter, but it basically doesn't matter what new technologies you matter. I think people are very, if you go above 10 gigatons, you're in big trouble. But that said, you know, I'm all for, you know, tripling, quadrupling the R&D budget. It's one of the 5 or 6 things that we ought to do. I wouldn't zero out the hydrogen budget. It's, I think, obscene that it's going up 50% while the overall efficiency budget is going down. But I just think, you know, every 5, 6, 7 years you wait, it's another wedge that you have to add, and that's and in an optimistic, you know, world. So as long as people are advocating hydrogen not to lead people into thinking that it is a deus ex machina literally, but is in fact a post-2040, post-2050 solution, that's totally fine with me. But that's not what this administration is using it for, that's not what General Motors is using it for, and that's not what a lot of other people have been using it for.
We have one last question.
Thank you. Jeff Koss of Stanford University. I'd just like to refer back to the last slide you showed, which is quite sobering in terms of the budget for health and medicine, I think it was. And I think part of the reason that it is, at least in my opinion, it is growing the way it does, it comes back to something that Steve Schneider was saying earlier, and that is, when it comes to our own personal health, I think we understand risk and reliability very well, and we've communicated that understanding very effectively to both business and to the government, and that's why it reflects in there. when it comes to climate change, I don't think we've done a very good job of communicating what climate change and the implications are to each one of us personally. I don't think people understand it on a personal level. They understand cancer, they understand tumors because they've seen people around them, perhaps family members, perhaps themselves that have experienced it. Whereas climate change looks to be some glacier 10,000 miles away that's melting. And so until we do that effectively, I think we're missing a big opportunity. And so even though I'm a technologist and an engineer, I think part of the efficiency equation is dealing with human behavior and changing consumption, changing the concept of affluence. And I think until we deal with that in an effective manner, all this talk about adaptation and technology coming at the 11th hour to our rescue and putting particles in the atmosphere and trying to mitigate, I think, is just not going to get there. Fundamentally, we have to understand things on a personal level, evaluate the risk, make choices, and change behavior until we're going to win this struggle. Thank you.
Well, I appreciate that comment. I mean, I think that as my thinking and speaking has evolved over the years, I now obviously spend a little more time talking about what I think the impacts are of doing nothing. These impacts aren't certain, but I now tend to think that they're probable. But, you know, the world will be driven to the kind of behavior change you want either voluntarily or by reality. And, you know, when I say after 2025, there's nothing we can do. That's, of course, not entirely true. We could just do what we did in World War II. You can just set up a board, and the board can come in and say you can't drive these. I mean, if you want to go down to 50% below current levels, now you have 5 decades, you know, to do it gradually and intelligently. If you go up 50% in 20 years and then want to go down 80% in 25 years, obviously it becomes very unpleasant and you get that sort of behavior change. So it seems to me the only possible way to avoid, you know, the grim outcome is to get leaders who are willing, and I include scientific leaders who are willing to be very blunt, but also lead, you know, to a different path. But, you know, I take your point very well.
Thank you, John. So I have a suspicion that the reason we have such a great audience at the end of the day has at least something to do with the fact that we were all looking forward to hearing from Art himself. And before I introduce him, which seems rather silly at this stage, but before I do introduce him, I would like to take a moment to acknowledge some of the people who are behind the scenes in making this event happen. Particularly, I'd like to thank Adrian Hink, who has done absolutely yeoman work in organizing all of the logistical aspects. And John Wilson, who is the assistant to Art, I guess, and is the chair of the organizing committee. And there are many other people who deserve thanks, and I just don't know the whole list, so I'm not going to venture there. But I also do want to express my thanks to each of the speakers, because the talks were extraordinary. I actually am only disappointed that I had to be paying so much attention to making sure the process ran that I could only listen with one ear, but I'm going to take the slides home and look over them again. Okay, so Art Rosenfeld. You know, we named this the Energy Symposium, the Rosenfeld effect, and you've heard a lot today about the Rosenfeld effect, and I guess one way of looking at it is the slide that's been shown several times already that illustrates the trajectory of California's energy intensity versus that in the country, especially with respect to electricity. One thing that we have not heard as much about, and so this is what I'd like to focus my introductory remarks on, is Art Rosenfeld's influence on it's like the community of people who are concerned with the sorts of issues that we talked about today. His influence on us because of who he is and because of the work that he's undertaken and because of the way that he's undertaken that work and because of the nature of the person that he has proven to be in that effort. Now, in reflecting on this, I realize that I'm really not the best person, but here I am. So I'm going to have to do the best I can. I'm not the best person because Art was always, I've known him for a long time, since 1979, but he was always one step removed from the people that I interacted with. He was the guy in the corner office who ran the Energy Efficient Buildings program when I was an undergraduate student in the physics department, hired to be a research assistant. He's actually co-author on my first paper, which is really important to me, but it was, one of 137th in Art's distinguished career on the way to getting 300, I don't know. I suspect that if one looked at all of the people that Art has influenced and lined them up in terms of the sort of scale of influence, I wouldn't be in the first 100. I might not even be in the first 1,000 because I don't know all of those interactions that you've had, Art. But I do want to say that even in my low status in that respect, the influence has been significant. It's been profound. I've been strongly struck by Art's diligence, his integrity, his commitment to a vision of trying to make things better, his lack of I don't know, any kind of pomp, his willingness to ask the stupid question and not care that he looked stupid in asking it, because he didn't really look stupid and he knew that. But when I was a student and, looking up at the mountains around me of the intellectual accomplishments, that was really influential, to see that kind of behavior in a seminar type of setting. And he was one of a handful of people who kind of shaped my understanding of what it meant, what it means to be a scientist. His commitment to his work, his hard work in carrying it out, his dedication, his diligence, and the other thing, I guess, that I really admire, and maybe I admire it because it's the sort of thing that maybe I'd like to be more of and I'm not, is the person who's willing to get out of the ivory tower and engage with the society where they are to make a difference, to take the science, to really, in the words that we use in ERG, to be that scholar activist, the person who works hard to get the science right, but then tries to do something with the science. If you do not know everything about Art's history, and I bet you don't, I would commend to you the memoir that he wrote in 1999 in the Annual Review of Energy and the Environment. 50 pages, there's like one major idea per page, so that's why I'm not even going to try to tell you everything that's contained in this. It's remarkable how many things I know about that are important that I didn't realize Art was responsible for, at least in part, and in fact, he was. Art, thanks for being who you have been and for continuing in that role. I'm going to choke up pretty soon now, so why don't you just get up here and take over, and I'll get off the stage. Get you on, and then I'll sit down. By the way, we've been timing each of the presentations, but the clock is officially off. Art can speak as long as he would like.
I don't believe you. I made up the transparency slides that go with this before I heard about the Fermi Awards, so I'm going to say a few things first. But just trivia. Because I think it's dramatic, and Steve Schneider or Joe Rome can tell me if my memory fails, he was talking about hurricanes. I remember maybe 10 years ago looking at, I guess they call it isotherms, or the map of the Middle Atlantic. And it was probably for 2 times industrial CO2 for 550. And as I remember it, the line, what's the magic number for hurricanes, Steve? What's the temperature? 26. And he says the depth matters, and I don't know all that. The 26 line ran through about Cuba. So hurricanes below there did fine, and then they attenuated before they hit Charleston. As I remember, for twice industrial, the line goes through Long Island. So when you're talking about triaging cities, and Joe Rome lives in Washington, D.C., which is south of Long Island, as I remember, we're in deep trouble. So a remark just about Adrian and John Wilson. I'm on the CC list, and the number of emails over the last 3 weekends, which have started at 7 o'clock on Saturday morning and gone on through 5 o'clock on Sunday evenings, is just amazing, and thank you guys. Particularly Adrian. A sort of serious comment about all the hype that went on, particularly with my 3 women friends from NRDC this morning. A hell of a lot of stuff I had little to do with was put in my name, and I disclaim all that, of course. But what I do want to say is to talk a little bit about the marvels that all of those facts did happen in California. I didn't do them, but they did happen. And I think if my career had a big piece of good luck in it, it was getting started around 1973 at the time of the embargo. Incidentally, a side remark which I make a lot is I think it's sort of ironic that all this modern energy efficiency and really the quantitative environmental movement as we now know it was all started by a bunch of OPEC, basically Arabs, who don't care at all about all these environmental issues, but who triggered this enormous and wonderful response. Anyway, the unsung heroes whose names didn't get mentioned today are the people who created the California Energy Commission. It was Charles Warren and Joe Alquist, who starting around 1972, before the embargo, looked, well, I don't know if it's entirely Warren and Alquist, but their aides in their offices looked at the rate at which power was growing in California, which was, I think, 6% a year, and did figure out that by today, at 6% a year, as somebody said nicely this morning, we would have 1 gigawatt every 8 miles from San Diego to San Francisco. And that was clearly unacceptable. And they dreamed up the Energy Commission to take a look at all sorts of wonderful things that they visualized. They gave the Energy Commission the power to do appliance standards and building standards, and they encouraged the utilities to adopt energy efficiency programs. What has been quite wonderful has been the Northern California Triangle. I mean, the Berkeley campus and Lawrence Berkeley Lab were very lucky that they were 15 miles from the Public Utilities Commission, which took this all seriously, and 70 miles from Sacramento, which took all this seriously. One piece of history which I do remember is that, as I remember, the California Energy Commission enabling legislation was first introduced in the spring or summer of 1973, before the embargo, was vetoed by then Governor Reagan as dangerous social engineering. The governor was then trumped in the fall by the Arabs. The same bill was presented and the governor signed it, and we were off to the races. But the three-way communication, that is, the fact that, well, I'll give you my personal example. We wanted building standards, but we didn't have any public domain computer programs with which to calculate building standards. Well, I was able to go to the CEC and get my first $250,000 to work on a program which became later known as DOE2. Within a few years, I was able to testify on behalf of the Energy Commission that this program really worked, and building standards started going into effect. And the connections have been wonderful. I was, with Dave Goldstein's help, able to convince Governor Jerry Brown that appliance standards, in particular refrigerator standards, wouldn't cost anything because there were no labels on refrigerators, and it turned out that the efficient refrigerators didn't cost any more than the inefficient ones. So standards would really require, at first, as a first stage, not a lot more than just labeling. So the combination of those two institutions for 30 years and research on the Berkeley campus and at LBL have really indeed contributed to this wonderful wedge between California kilowatt hours per person and the United States. As one example, just because Steve Schneider talked about compact fluorescence, there's a good example where Steve sort of implied that I had something to do with it. In fact, it was Sam Berman who did it. Sam, where are you? There. And Sam was very courageous. I had a professorship on campus, and I had a lab at LBL, and I didn't have to take any risks whatsoever to start the Center for Building Science. Sam gave up a perfectly good professorship in Stanford to come over here, and indeed, on his first, what was it, two contracts for $50,000, jump-started first the high-frequency ballast and then compact fluorescent lamps. And I think the factor of 1,000 is pretty good payback. That wasn't the payback to society because the lamps cost something, but it was the payback for government research. I think worldwide, compact fluorescent lamps today are saving around $10 billion a year. I don't know by how much Sam advanced this. Let me guess, 5 years. So $10 billion a year for 5 years is $50 billion. Each of those grants was $50,000. The payback is pretty interesting, as Steve said. Which leads me to my next quantitative remark. And this has something, I mentioned this because it has something to do with the Fermi Award. I heard about this award about a week ago. I got a phone call from the somewhat maligned now Secretary Bodman. And they were nice enough to send me the press release, which was in the paper the last day or so, to check some facts. Now, here's the interesting point. Secretary Bodman was quoted as saying that our community, the folks in this room, were responsible for a set of processes and hardware which are saving the United States, quote, hundreds of millions of dollars per year. Someone called him back up and said, "You mean hundreds of billions, don't you?" And they said, "Oh yeah, well, a factor of 1,000, you know." I'll show you some slides, and you've seen numbers from refrigerators alone, in the United States alone, as being worth something like $17 billion a year. So the hundreds of millions, you know, wasn't very hard to overcome. But I don't think we've done a very good job in putting the whole story together. So I want to quote a couple of numbers from a memo. I don't think he even bothered to publish it, from Skip Leitner from EPA, who once a year, along with ACE3, puts out sort of score sheets. And a very brief summary just goes like this. First of all, let me remind you that this year's energy bill, electricity, gasoline, natural gas, and so on, was $1 trillion. So it's about 9% of our gross national product. Incidentally, when those elder ones of us, including Rob and I, got started, energy was 12% of GDP. We got it down a couple of years ago to 6% of GDP. Prices have escalated. Henry Kelly would say that's good. We're getting back to some public attention. We're back up to 10% of GDP, but that's because of price hikes, not because of lack of energy use. In terms of energy use, the measure is usually called energy intensity, and it's energy, millions of BTU, primary energy, per dollar of gross national product. It's, of course, gross national product which drives energy use. You have more money, you buy a new car, it's going to use gasoline, it has embedded energy, and so on. You buy a new house, it has embedded energy, it's going to use electricity, and so on. So the measure to look at is energy over GNP. In the last 30 years, for the United States as a whole, and California has done better, E over GNP has dropped from 100% in 1974 to 58% today. That's pretty damned impressive. The naive thing to do would be to say, well, if 58% corresponds to $1 trillion per year, then 100% would correspond to nearly $2 trillion a year, and we've saved $1 trillion. That's not correct, because inexorably technology makes things better anyway. But I think it's fair to say that before 1973, when we sort of got our act together, technology had only been bringing down energy over GNP by 1% a year. All the models at the time took 1% a year as a so-called exogenous improvement. Since 1973, we have come down 2% a year in the West, in the United States. So we've gained 1% a year for 30 years, which is e to the 0.3, which is 35%. And so instead of $1 trillion a year, if we were 35% higher, that really would be about $350 billion a year. I think that's an honest estimate of what we've accomplished since 1973, $350 billion a year. Now, that doesn't mean that we get credit for all of that. Some of it, of course, is just an acceleration of a trend which probably wasn't very clear before 73. We've gone faster and faster from smokestacks, which use a lot of industry, a lot of energy, to chips, I guess, which save a lot of energy. So probably half of that effect is structural. And some of that effect is automobiles. We went from 14 miles per gallon to 28 miles per gallon. And I don't think a lot of us in this room, maybe Steve Nadell accepted, have done much about transportation, so I'll throw some of that away. I still think that the buildings and industry part that Rob Socolow talked about is good for $100 billion a year today, Mr. Cheney notwithstanding. The only other remark I think I'll make of local color before I show you some slides is people, of course, ask me how I feel about the Fermi Award. And I'm pretty overwhelmed. I'm not in tears right now on this platform, but I'm pretty overwhelmed. But since we're talking about California, I did think that the institutions around here can take some pride. I printed out the list of Fermi Awards, and I wrote C's against those people in the last 50 years who've gotten Fermi Prizes. And it's pretty impressive. 1959, Glenn Seaborg. Oh, I'm going in the wrong direction. 1957, Ernest Lawrence, certainly deserves it. 1959, Glenn Seaborg. I've dropped the dates, I'll go faster. Teller, Oppenheimer, Panofsky, Louis Alvarez, whom I regret not working for, my other mentor, Harold Brown, and then since 2000, Sid Drell, Herb York, and Seymour Sack. Of those, roughly 10, I think more than half are from the Berkeley campus or from Livermore. So I think we can feel pretty good about all that. Okay. What I think, that John Wilson and the steering committee had in mind when they gave me this thing at the end called Summing Up was that I was somehow or other supposed to sum up some of the wisdom from today, but I'm not going to do that. Instead, I'm going to show you a few slides of what of either publications or dog-eared slides that I'm particularly proud of, and make a few comments about them on the way. Page down. This is, of course, the one I treasure most. It sort of got me started. Nuclear Physics, a course given by Enrico Fermi with O'Rear, Rosenfeld, and Schluter. You can see whose name they wanted to put more prominently. Whoops, page up. Whoops. I think I won't say anything. Well, yes, I think I will. One of the things that was amusing about this book was how badly the beginnings of my inability to estimate the future. This book eventually went to 7 editions and 30,000 English prints alone. One amusing thing was we kept getting notes from our friends about mistakes in the program. I can tell you, based on good statistics, we got mistakes out about 1/E per edition. There were still a lot at the end, I'm sure. This is the book that Rob talked about, Efficient Use of Energy. It was really an enlightenment. You know, we started off with Rob being host at Princeton, trying to understand why the United States used twice as much energy as Western Europe or Japan. And I think we thought it was going to be fairly technical. I think it took me and probably Rob about 2 days to recognize that the answer was really pretty simple. Energy was dirt cheap compared to Europe and Japan, and what's dirt cheap tended to get valued like dirt. And there were a hell of a lot of things we could do. In that book, and Sam was important in this page 2, the chapter that didn't get mentioned. I think he already talked about compact fluorescent lamps and high-frequency ballasts. I think I wrote the one on Windows. Maybe Sam did. I don't know. Sam did. Sam did. In which we said that the loss of heat, in that time we were thinking only about wintertime. There wasn't so much air conditioning. The loss of heat to American windows every year was about equal to what was expected from the then forthcoming Alaska pipeline. And we got low-E windows, and we saved 3/4 of that. And it was a wonderful book. It was the most popular physical society book for many years. Page down doesn't work. Well, oh, okay. Beginnings of ACE3. Again, I want to say that this was the beginnings of the. You know, I'm doing up arrow and down arrow. Here, I'm going to try page up. That doesn't work either.
You have another controller which you can try.
A backup.
Sorry, that's back. Yeah, the upper one is forward.
This was, thank you, Bill. This was the beginnings of the Princeton Berkeley axis. I think Bob Williams and I alternated as chair and president, I can't remember what, for 10 years. And Steve Nadell's here to represent a still very healthy ACE3. Thank you, Steve. Page down. This one is a particularly interesting story. During the waning years of the Carter administration, John Sawhill got some money to do a study at CERI. Henry Kelly, who's here now, was then the associate director, called the CERI Solar Conservation Study. we looked into two issues. One was it possible in Carter's second term, because he was campaigning, to get 10% solar in another 4 years? The other was, were we building too few or too many power plants? We had about finished this when Reagan swept into office, and the draft said, A, there was no way of going 10% solar in the next 10 years, which probably Reagan would have liked. But the other said, we're building 50 gigawatts of power plants, too much. Demand is not going to go up that high. We based this a little bit on experience in Europe and Japan. The Reagan transition team took one look at the draft, which was around the office in DOE, and called us all individually and said if we even sent this damn thing out for review, we would all be fired. And just to make it clear, they met Dennis Hayes at the airport in Denver and fired him. And Henry went back to OTA. Well, then we were stuck. We had this valuable report with what we thought were good things, and we weren't even supposed to send it out to review. What the hell to do? So Henry called up the man, Congressman Dick Ottinger, who had arranged for the funding in the first place, and said, what the hell do we do? And between them, they decided this was really easy. Ottinger would hold hearings. The book would get published as a committee print. That brought it into the public domain. Brickhouse Press picked it up, and we got a little extra publicity as banned in Washington. And, and I'm pleased that it was one of the early books which used the word sustainable. Am I close enough to the mic? Can you guys hear in the back rows okay? Back up? How's that? Thank you. Alan Meyer's here, so I want to show his thesis, which developed into this great book. First book to do conservation supply curves, which are now used, I think, as a universal tool for calculating benefit-cost ratios. Thank you, Alan. That's a conservation supply curve. I won't go into it. This one was interesting, National Academy Press, because it was the first time we got really a serious bunch of economists to admit that the marketplace was not yet perfect and that there were things one could do that saved money. We didn't get all of them. There's a famous footnote on about the third page by Nordhaus from Yale, basically saying he still wasn't completely convinced, but that since 9 out of 10 of his colleagues went along with it, he would grudgingly go along. This is the one, who referred to this today? Oh, Mark Levine. This is the famous 5-lab study. Oh, Joe Rome referred to it too. And I think it's fair to say that Clinton really believed that this was the report which gave him the courage to send Gore to Kyoto. There was some considerable question as to whether the United States was going to send that high level of person. Now, you may tell me Kyoto wasn't a great success in terms of the Americans, but I think it's a good thing that Gore went, and so that was a great piece of work. This was a Joe Rome piece of brilliance to organize. It's the 5-lab study, because if we tried to do it within DOE, we would have never been cleared for years after Kyoto. I want to show this one with a laser pen. This is an actual transparency which Pat McCullough scanned for me, and it's the first time Dave Goldstein and I really tangled with Pacific Gas and Electric, which got referred to today too. The Energy Commission had just been formed. The date for this thing was December 1975. The Energy Commission came into being, I think, in early 75. Oh, come on. I'll page back. I better not touch that. This was the rate of growth of peak power in California up to the embargo. The Energy Commission then polled the utilities and said, oil's gone up in price, and of course we were half on oil in those days, and natural gas is probably going to go up in price, and what's going to happen in the future? And the utilities scratched their heads and decided that growth was going to drop from 6% to 5%. Well, we had just worked on the famous Princeton building study, and we didn't know a hell of a lot about buildings in that time, but we knew something, and we knew how a refrigerator worked. And David and I decided that we ought to be able to keep electricity use per capita constant. And the big uncertainty was how fast electricity growth, population growth was going to grow, but we said whatever it does, we'll keep constant. So our prediction was along these lines, which was, we defined as the potential. The open squares are what actually happened. In between, there were some interesting things. The chairman of PG&E did call the president of the university and said that David and I were completely incompetent and unqualified and should both be fired. And I remember the answer was, I think it was Charlie Hitch called me up and said, there are two things that he told PG&E. The first one is that as to firing graduate students, they pay us. We don't pay them, and it's hard to fire them. The other thing he admitted was, he said, there are physics professors who are a lot more troublesome than Rosenfeld, and if I could fire a physics professor, it wouldn't be Art. Now, what has actually happened, page down. This is the same curve, but brought up to time. This is the 5% growth period, and if it continued, we would have been up here today at 120 gigawatts. We're actually at 55. So in this long scale, here's what we've actually done. It's been constant per unit of population. So instead of 120 gigawatts, we're at 55. That's pretty satisfying. And if we do it per capita, this is this famous plot, my favorite plot. Pat McAuliffe made this plot and updates it. Pat, are you here?
I should admit so, but yeah, I am here. If you want the copy, it's available.
Oh, while I think of it, I guess all these proceedings are going to be on the website. So, and John Wilson got them done per person, so you can look up everybody's slides. But John, are the slides themselves going to be available so we can steal one another's slides? Yes, and the slides will be available. Okay. A disclaimer. I want to go back to that. The big question, of course, is how much of this effect is structural, just because the weather's nicer in California, and how much of it is policy. And Pat and I think that about half of it is policy. So what I want to say is, this line is flat. This line goes up 2% a year. Probably the actual gains from policy in California are about 1% a year. That's still pretty good. If the rest of the world would follow that, to quote Rob Socolow again, we're only going up 1.5% a year in CO2. If we could add 1% a year worldwide, we would be making giant steps. So this is the policy part of what's worked so well in California. Of the savings, which turn out to be approaching 1% a year, the part we can account for, like a quarter come from appliance standards, a quarter come from building standards. I'm enormously pleased with these standards. We update them every 3 years. We're so enthusiastic that we are even suing the Reagan administration. I'm sorry. My prejudices are showing. We are even suing the present administration. Over the same issue, David, all right. Because what happens is that the feds are responsible for about 20 or 25 building standards. They're supposed to be regularly updated. That would be about 4 a year. The Bush administration has been in office 5 years, and the only thing it has done has been to retrograde one standard for air conditioners from 13 to 14, but the courts put it back. So what we tend to do then is to take the things which the feds don't preempt us on and make our own standards. And then there are the utility programs. This is 1% of your electricity bill per year has been plowed back for the last 30 years into what are called efficiency programs. They are designed to beat the standards, make a transition in the market, put new products into the market, so that pretty soon they are accepted enough and of volume enough to go into the standards. So it's a marvelous closed cycle in which we have an R&D program. We then enhance market acceptance of new products, and then we put them into the standards, and once we put them into the standards, they don't cost anything, and we go on to do new stuff. That's energy, that's in billions of kilowatt hours, that's in megawatts saved. This is, I said honestly, I would just talk about my most successful slides. This is one which is actually originally done by Dave Goldstein, and it's the unbelievable progress in refrigerators. This is a plug for appliance standards. From 1947, going up, let me get rid of the purple line. That's the size, going up very fast, limited by the kitchen door, and then a little bit of breakthrough here. This is electricity used by refrigerators going up completely out of control until the embargo, and then this enormous right-hand turn, which was appliance labels and then the threat of standards by the Energy Commission. All of this decline down to here was California standards. During Mr. Reagan's tenure, there wasn't a lot of enthusiasm for federal standards. And then the feds got in the game, and we're down here to a quarter. One of the things I'd like to point out is this represents a 5% gain per year for 30 years. People will keep asking, have we used up all the low-hanging fruit? Well, the returns on investment aren't as good here as they were before, but it's still 5-year return on investment every year, and the technology gets better. So we seem to be a long way from physical limits on refrigerators, air conditioners, cars, whatever you want to name. Dave Goldstein contributed the following interesting addition to this plot recently. This is the retail price of refrigerators. Now, every time we make a refrigerator better, we're supposed to say, well, we add $1 to the first cost, but you get your money back and save electricity bills in 5 years, and then you're laughing all the way to the bank for the next 10 years. What actually happens is you tell the manufacturers they have to updo their assembly lines. They then put all this inexorable progress that's happened over the last 20 years, if the line's 20 years old, and the price of the retail price of refrigerators, instead of going up, comes down. So I think it's fair to say that we have not run the price of refrigerators off the roof. We have not ended civilization as we know it. It's really all worked quite well. Energy saving, okay. This is how much energy we would have used if refrigerators were at 1974 efficiencies. This is how much we actually use. This is the savings, and I only want to make 1 point on this one, wrong way. I want to make 1 point on this one. This is the savings scaled down in billions of kilowatt hours. This is all the hydro in the country, Columbia River, Tennessee River, whatever. This is the environmental impact. And this is nuclear power in this country. Refrigerators are about 1/3 of it. If you do it in dollars, however, you have to remember Well, I think I'll point here. You have to remember that this stuff is at your meter where electricity is worth like 9 cents a kilowatt hour. This stuff here is at the bus bar somewhere on Bonneville Dam. It still has to be transmitted, managed, distributed, handled, and all that. So this stuff is worth 3 cents a kilowatt hour, and the nuclear is only worth about 3 cents a kilowatt hour. What you end up with then in dollars, contribution to economic growth, refrigerators about $17 billion a year. All the hydro in the country is worth about 8, and all the nuclear stuff in the country is worth about 20. So a couple of more updates in refrigerator standards, and we bypass nuclear power. The problem is there's not a lot of profit in refrigerators, whereas there's a lot of money involved in nuclear plants. So everybody's heard about nuclear power, and people haven't heard a lot about refrigerators. This is the same thing for the Three Gorges Dam. Wow. Three Gorges Dam. Phooey. Three Gorges Dam. This is the value of all the electricity sold in China from Three Gorges Dam. This is the value of 10 years of sales of the new, thank you, Mark Levine, of the new refrigerator and air conditioning standards. I only put 2 to 1 instead of 3 to 1 because for some miracle the Chinese claim they can do transmission and distribution cheaper than we can. I don't think I believe them. But even at 2 to 1, this is contributing twice as much to the Chinese economy as the Three Gorges Dam. And luckily, they're beginning to talk about more appliances and tougher standards. Okay. I'm going to quit in 1 minute, but I do want to show this plot and talk about cool roofs for just a moment. This is a plot of Los Angeles temperature from 1880 to 1950, and then going back up again. Forget the snaggletooth here. That's Krakatoa blowing its top and cooling the world for a few years. Oh, come on. I wasn't touching. Well, maybe I had my hand on the computer. What you see is a 10-year rolling average of the local temperature in the summer. I don't know, August, I think. No, the annual high for the summer, coming down from 103 to 98 as we brought in Colorado River water, introduced Orange County, and evapotranspiration. Then we started tearing up the orchards and putting in asphalt roads and houses with dark roofs. And we're now back up 7 degrees. Some of that is going to be hard to fix, but the roofs are pretty easy. Hashim Akbari is here. He and I started the Heat Islands group in Berkeley about, I don't know when, 1982. It's been a long pull, but starting in this past cycle, 2005, in California, new buildings and major retrofits, if the roof is flat and there are no architectural issues, do have to have a white roof. That saves like 20% on air conditioning bills. Even more interesting is that technically now it turns out you can make cool colored roofs. And page down. Here are tiles which you can buy in California today, and you don't know you're getting the cooler one. Here, for example, is terracotta. Well, let's look even at black. Normally, black is only 4% reflective. This is 41% reflective black. The trick is to use pigments which are whatever color you want in the visible, but which are highly reflective in the near infrared. The cost is nothing. The savings in air conditioning are significant. And so starting in 2008, all new roofs in California will have to be cool but colored even if they're visible, sloping. Amusingly enough, Hashem and I have realized that in addition to saving worldwide tens or hundreds of millions of dollars a year air conditioning load, that's just the roofs on buildings. But car air conditioners are very inefficient. And we can do the same trick for cars, and it turns out it looks like a 2 or 3% gain in fuel economy. And it's interesting that this is a beautiful example of win-win, because if you have a car with a cool roof, then it doesn't get stinking hot in the sun. So then you can downsize the air conditioner. So then you can reduce the first cost of the car. But you also get a 2% gain in fuel economy. So seems like a good way to go, and I've enjoyed all my years of working with Hashem. And the reception's supposed to start, so I'm quitting. Thank you.
Make them stop.
What can I do, Art? Art's first words to me when I came up here was, make them stop. And we also agree that it's been a long day, and so we're adjourning on Art's last words, and wish you all the best, and thank you for your attendance today.
Thank you, Bill. It was wonderful. And you really, I mean, apart from me, you